Okay, hello everyone, welcome back to another video. Today we're going to be looking at a really interesting proof involving contour integration for Euler's reflection formula for the gamma function, which tells us that gamma of x times gamma of 1 minus x equals pi over sine pi x. Now you might be wondering how we could approach a question like this using integration, because there doesn't look to be any integration immediately present. But given that I know that a lot of my viewers like integral videos, we're going to be doing it today using contour integration, and we're going to be starting with the beta function. And that's because the beta function has a lot of relationships to the gamma function which make it useful. The one that we're going to be using today is that beta of xy is equal to gamma of x times gamma of y divided by gamma of x plus y. And we've just got to keep in mind that this is for the real part of x and the real part of y being greater than 0. Now, this is where we get our reflection formula from, because all we have to do is let y equal 1 minus x. In doing so, we know then that beta of x 1 minus x is equal to gamma of x times gamma of 1 minus x divided by x plus 1 minus x, well, divided by gamma of x plus 1 minus x, which is just gamma of 1, which is 0 factorial, which is 1. And so we don't have a denominator anymore, which means that evaluating beta at x and 1 minus x is the same as evaluating gamma of x times gamma of 1 minus x. So that means all we've got to do is find a nice integral formula for the beta function, and we can evaluate gamma of x times gamma of 1 minus x through that. Now, the one that we're going to choose to look at today is the following: that beta of x 1 minus x is equal to the integral from 0 to infinity of t to the power of our first input, which is x, divided by 1 plus t to the power of our two inputs added together. Which of course might reveal to you why we've chosen this integral representation. It's because x plus 1 minus x is just 1. And so we just have a denominator here of 1 plus t, and of course we're integrating with respect to t. Now when you look at this integral, it will become immediately obvious why contour integration comes to mind. We're taking our limits of integration from 0 to infinity, which fits perfectly with a contour that goes along the positive real axis, and we've got obvious poles in our denominator, but we're going to get into that in a minute. So now that we know what we're integrating, let's define our complex function f of z as z to the x minus 1 divided by 1 plus z. And we can instantly see it's going to have poles. A pole, for anyone who isn't aware, is a place at which a function becomes undefined and blows up. In our case, that's going to happen as z approaches negative infinity and the bottom of this expression approaches 0. So we've got a pole at z equals minus 1. But there's one other thing that we have to consider, that's are there branch points and branch cuts. These are places where our function might become multi-valued, which can happen in the complex plane, and we have to avoid these points if we want to take our limit through them, because otherwise, after doing a rotation around a point, we don't return to where we started, and that's a big problem. So we've got to consider what's going on in our function. Well, given that x is between 0 and 1, x minus 1 is between negative 1 and 0, and that means that we're going to have fractional powers as possible inputs of x. We can't guarantee that x minus 1 will be an integer. And this means that around 0 there's going to be a critical point, because our function will become multi-valued. I'll leave it to you guys to think about, but it's to do with the fact that we deal with all powers really as e to the power of something times log something when we're looking at complex numbers, because that's the way to best understand them, and that becomes very difficult when we're not looking at integers. So we've got a branch point at z equals 0, and therefore we need to implement a branch cut. And given that our pole is at negative 1, we don't want it to be along the negative part of the real axis, but we do want our branch cut to go along the real axis because that's where it's easiest to parameterize along. So I'm thinking we'll put it along the positive real axis and we'll let it approach out to infinity from 0. So I think this means that we're ready to draw our contour. And of course, this is the imaginary axes, this is the real axes. And first thing that we're going to note is that we have a pole at -1. Second thing we have to note, we've got a branch point at the origin, and we're implementing a branch cut along the positive real axis. And we've got to find a contour that's going to capture our pole, so we can use Cauchy's residue theorem, but that avoids our branch point and branch cut. And it seems that the perfect contour to do that is a keyhole contour. So we're going to travel around this branch point to avoid it, but along either side, we're going to go out to infinity, and then we're going to circle back round like so. And I'm going to name each part of our contour so that we can refer back to it over the course of the video. Our big curve here, I'm calling capital gamma. Our little curve here, I'm calling lowercase gamma, but I'm going to put a little negative sign there to remind us that it's in the negative direction. Our big gamma is anti-clockwise, which is fine, but our little gamma is going clockwise. And then of course we've got our two real parts here. I'm going to say that the radius of our big circle is capital R, and of our little circle is epsilon. So keep this image in mind. I'm not going to have it on the board for the entire thing, but take it all in. This is what we're going to be integrating along for the rest of the video. I will draw quickly a little version in the corner just so we can refer back to it when we need to. So let's state what we know. We know that the integral around the entire closed contour is equal to 2 pi I times the residue at f of z at -1. Of course, it would be equal to the sum of the residues if there were multiple, but there's only one that we've captured within our contour, and so that's all we're worrying about. But it's also equal to, and excuse me for not writing out f of z every time, I want to save time here. It's also equal to the integral along big gamma plus the integral along little gamma plus the integral from epsilon to r, and then plus the integral from r to epsilon. This part is going around, this part's going on the other way, this part's getting us from big to little, and this part's getting us from little to big. And we're going to evaluate each one of these, and we're going to hopefully show that as we let our radius r approach infinity, and our radius epsilon approach 0, capturing the entire of the positive real axis, that both of these integrals along gamma and little gamma will be 0, and that will leave us with something really nice to look at. So let's look at the integral along big gamma first. Well, we want to parameterize. We're looking at our curved part here. We've got a constant radius of r, and the only thing that's changing about our points along this is the argument. We're just changing the angle, not the radius. So we're going to parameterize with z equals r e to the I theta, bearing in mind that theta is between 0 and 2 pi, given that we've made our branch cuts. This means that dz is equal to I r e to the I theta d theta, because we just differentiate e to the I theta, and we multiply by the derivative of I theta, which is I. So our integral along gamma is also the same as our integral from 0 to 2 pi of r to the x minus 1 times e to the x minus 1 I theta times r e to the I theta d theta divided by r e to the I theta plus 1. And I've just gotten this by swapping out all of my z's for r e to the I thetas, by multiplying by our differential part, and by swapping our z in the denominator out for an r e to the I theta. Now the first thing that I notice here is firstly I is a constant, I'm going to pull it out of my integral, and secondly that I've got an r to the x minus 1 times by r, and an e to the x minus 1 I theta times an e to the I theta, which means this whole numerator can be written much more nicely as just r to the x times e to the x I theta. And now I'm going to use quite a common technique that's used within contour integration. I'm going to take the absolute value of my integral, and I'm going to say the absolute value of the integral is less than or equal to the integral of the absolute value. So of course I can ignore I, because the absolute value of I is 1. And so the absolute value of our integral is less than or equal to the integral from 0 to 2 pi of the absolute value of Rx e to the x I theta divided by the absolute value of r e to the I theta plus 1 with respect to theta. So the absolute value of ex to the I theta is always less than or equal to 1, which means I can just treat this as 1. And that's because if we think about rotating around the unit circle, all that we're varying there is theta, and our radius is staying as 1. Our modulus is 1, and therefore we're not going to become any greater than 1. And the absolute value of r to the x is just r to the x. Given that r is a distance, it's positive. So now all we've got to do is worry about our denominator, and we're going to use the reverse triangle inequality, which tells us that the absolute value of a minus b is less than or equal to the absolute value of a minus b. But of course we're looking at a denominator here, and that means that our inequality sign is going to swap. Like so. So all we have to do now is choose our values of a and b carefully. If I let a equal r e to the I theta and b equal -1, we have something of the following form. And what does that tell me? Well, it tells me that this integral that I've written out must be less than or equal to the integral from 0 to 2 pi of r to the x divided by the absolute value of r e to the I theta minus the absolute value of -1. And this has a lot of simplification we can do. The absolute value of e to the I theta, as we've already said, is 1, so we can just take that as r. And the absolute value of -1 is just 1. So we're looking at the absolute value of r minus 1, but of course we're looking at r to approach infinity really, so we're not going to have to worry about absolute value of r minus 1 being anything that's less than positive, and so we can remove our absolute value brackets completely. Now we're looking at the integral from 0 to 2 pi of r to the x divided by r minus 1. Now we've arrived at a really good place because we're saying the absolute value of our integral along big gamma is less than or equal to something integrated from 0 to 2 pi, r to the x over r minus 1, with respect to theta, and we're doing an integral that has no thetas in it. So really this is all just a constant, and we're doing the integral from 0 to 2 pi of 1 with respect to theta, which is just 2 pi. And so this expression is equal to 2 pi r to the x over r minus 1. And we're now at a point where we're ready to let r approach infinity. So we're going to say the absolute value of I gamma is less than or equal to this expression here. And if we take the limit as r approaches infinity of 2 pi r to the x divided by r minus 1. Now both the numerator and the denominator are approaching infinity here, which allows us to use L'Hopital's rule. The derivative of r minus 1 is just 1, and the derivative of 2 pi r to the x is x r to the x minus 1. But now we're going to use that same inequality we looked at before. Given that x is in between 0 and 1, that tells us that x minus 1 is in between -1 and 0, which means that our power of r here is always going to be negative. What does that tell us? It tells us that we're always going to be having 1 over r to the power of something, because of course a negative power indicates we're taking the reciprocal, and that puts us in a good position because 1 over anything approaching infinity is going to approach what? Well, it's going to approach 0. So we now know that the absolute value of I gamma as r approaches infinity is less than or equal to 0, which implies that as r approaches infinity, I gamma is equal to 0. And that's of course because the absolute value of I gamma couldn't take a value less than 0, so it must be equal to. Now we use a very similar argument when we're integrating along little gamma. So similar in fact that I'm not going to go through the entire process again. I'm going to leave that to you. The only difference between our two contours, the parts of the contour that we're looking at, is that with big gamma we're going anti-clockwise and with little gamma we're going clockwise, and there's of course a difference of radius as well. So apart from swapping all our r's for epsilons, we've just got to worry about an extra negative sign indicated by the opposite direction. But since we start by taking the absolute value, this isn't going to affect anything. And that tells us that the integral along little gamma is also going to be less than or equal to 2 pi epsilon to the x divided by epsilon minus 1. And if we take the limit as epsilon approaches 0 here, clearly you can see that the top of our fraction approaches 0, the numerator approaches -1, and therefore the entire thing approaches 0, meaning that as we take epsilon to 0, this part of the integral will vanish. And this is fantastic. It means that the integral along the entire function is equal to, well, as r goes to infinity and epsilon goes to 0, 0 plus 0 plus our integral from r to e, which of course is going to be infinity to 0 of our function, plus our integral from 0 to infinity of our function with respect to z. But we can't just leave this here, we've got to parameterize. With this part of the function, this part of the integral is when we're returning from r to epsilon, just here in our contour. It's this part that takes us back to go round our point. And that means that this is after we've done a rotation of 2 pi. So we'll parameterize here with z equals, and I'm going to choose a variable t, e to the 2 pi I, which means that dz equals e to the 2 pi I dt. Whereas over here, we're going to have rotated around 0 degrees, so we let z equals t e to the 0i, and dz equals e to the 0i dt. So, rewriting our function using this parameterization, we've got the integral from infinity to 0 of t to the x minus 1, e to the 2 pi I, x minus 1, times e to the 2 pi I with respect to t, divided by 1 plus t e to the 2 pi I. And over here we're going to have the integral from 0 to infinity of t to the x minus 1, e to the 0, x minus 1 I times e to the 0 I with respect to t, divided by e to the 0 I times t plus 1. Now over here our zeros are really nice, right? E to the 0 times anything is just going to be 1, so we can ignore this entire part over here, and we can just treat this as 1 as well, which means that this part is the integral that we're looking to evaluate. This part here I'm going to represent with an IR, and that R represents real. Whatever the value of this is, that's what we're looking for. Now this integral is quite close to that, but there's stuff going on. Firstly, I'm going to notice that e to the 2 pi I x minus 1 times e to the 2 pi I is the same as e to the 2 pi I x. And secondly, I can take that out as a constant. And I know some of you may be thinking, e to the 2 pi is just 1, why are we treating this any differently? And you're correct, because of course our e to the 2 pi I over here in the denominator is just 1, and we'll treat it as such. And now we have ended up over here with our expression IR. And of course, bear in mind though, that the bounds of integration were infinity to 0, which means that we're going to put a negative sign in front to swap our bounds, which is a rule that we've spoken about before on this channel. So we've got negative e to the 2 pi ix times IR plus IR. Now, why did I treat my e to the 2 pi I differently here? It's because it's getting multiplied by an x in the power, which means that actually, for different values of x, unlike the exponents that we had here, which were all multiplied by 0, leaving everything the same, for different values of x, this e to the 2 pi I x could be different things, and so we've got to consider it differently. Now, after all our hard work, we know that the integral along the entire contour is equal to 1 minus e to the 2 pi I x times the integral that we're looking to evaluate. And as we said at the start, this is also equal to 2 pi I multiplied by the sum of the residues. So, what are the residues? Well, it's the limit as z approaches our pole multiplied by the factor that is causing our pole to blow up in the first place times by the function. Now, of course, we see nice cancellation here. That's kind of the point of what we're doing. And actually, what I'm going to do is observe that -1 is the same as e to the pi I. And so we're just taking the limit as z approaches e to the pi I of z to the x minus 1. And that's, of course, equal to just e to the x minus 1 pi I, which is equal to e to the x pi I times e to the negative pi I, and e to the negative pi I is just negative 1. So really we're looking at this entire thing being equal to 2 pi I times e to the pi I x. So let's create some space so that we can do our final bit of manipulation that we need. So summing up all this information that we have, we know that I of r must be equal to gamma of x times gamma of 1 minus x, which is also the same thing as negative, because of course we had that e to the negative pi I, 2 pi I times e to the pi I x divided by 1 minus e to the 2 pi I x. And anyone who's seen the complex definition of sine might suspect what's coming next. We're going to multiply by e to the negative pi I x on the top and the bottom of our fraction, leaving us with negative 2 pi I divided by e to the negative pi I x minus e to the pi I x. And we've got a negative here. If we get rid of that and then we swap the direction of subtraction in the denominator, we've reached what we're looking for. Because sine of pi x is equal to e to the pi I x minus e to the minus pi I x divided by 2i, according to the complex definition of sine. And that's exactly what we've got here, but flipped upside down, multiplied by pi. And that tells us that I of r, which is equal to gamma of x times gamma of 1 minus x, is equal to pi over sine pi x, or you could write it as pi times cosecant of pi x. So there we go, I hope everyone's enjoyed. This is a taste of a keyhole contour for contour integration. It's quite a classic one. And please let me know if you have any questions. If you'd like a challenge down below, you can try and prove the reverse triangle inequality and also explain to me why we have to make a branch point and a branch cut around 0 and then going off to infinity due to our issues with a complex power. Thanks for watching, and I'll see you soon. Bye.